This problem is internal vehicle dispatching inside a container terminal. Terminal trucks, also called yard trucks or hostlers, move containers between berth, yard storage, rail areas, and truck gates. Dispatching is real-time coordination under uncertainty. The objective is to keep containers flowing, avoid queues, and prevent expensive idle time at cranes and gates. In this scenario, a fleet of 15 to 25 terminal trucks moves containers between terminal subsystems. The dispatching system must decide which truck handles which request based on current truck location, container priority, and equipment availability. Uncertainty comes from ship operations, shifting gate appointments, equipment breakdowns, and weather impacts. Operationally, the dispatching policy must be robust. It cannot assume perfect schedules because reality changes minute by minute. This deck progresses from exact modeling to scalable and adaptive methods. Tier 1 is a minimum cost network flow formulation. Tier 2 uses an auction-based approximation algorithm. Tier 3 applies the Dragonfly algorithm meta-heuristic. Tier 4 uses self-supervised learning for predictive dispatching. Tier 5 uses an integrated digital twin. Tier 6 uses an autonomous multi-agent ecosystem. Tier 7 focuses on human and artificial intelligence collaboration. Tier 1 models truck and container movements across locations and time periods. Truck flow captures repositioning and availability, while container flow captures whether a specific request is served in a time period. The objective balances total travel time and weighted completion time for priority containers. Operationally, this means you do not only minimize driving, you also protect high-priority moves so service commitments are met. This slide introduces the sets and the parameter categories used by the model. Operationally, sets define the physical locations and the decision horizon, while parameters define travel times, priorities, and time windows that determine what is feasible. Parameters include travel time between locations, priority weights for containers, and time windows such as earliest pickup and latest delivery. Operationally, these parameters are the bridge from the terminal operating system into the optimization model. If time windows are wrong or priorities are stale, the dispatching plan will optimize the wrong work. Decision variables include the number of trucks moving from one location to another in a given time period, and binary indicators for whether a container is transported along a specific movement in a specific period. Operationally, the truck flow variables represent where capacity is, and the container flow variables represent whether customer and vessel commitments are being served. The objective combines total travel time with weighted completion times for containers. Operationally, this is the core trade-off. If you only minimize travel, you may ignore priority. If you only chase priority, you may create excessive empty travel and starve the rest of the system. Truck flow conservation ensures that trucks are conserved across the network. Trucks that leave a location must have arrived from somewhere, so the flow is balanced at each location and time. Operationally, this prevents impossible schedules where trucks appear out of nowhere or vanish. It also forces the model to account for repositioning decisions explicitly. This constraint ensures each container transport request is served exactly once within its allowed time window. Operationally, that prevents two failure modes: missing a required move or duplicating work. Both cause downstream disruption, missed appointments, vessel delays, or wasted capacity. This constraint links container flow to truck flow. The total number of containers assigned to an arc cannot exceed the number of trucks traveling that arc in that period. Operationally, this captures the basic physical limit. Each truck can carry a single container at a time, so container moves must be backed by truck capacity. Fleet size limits total truck flow in each period. Operationally, this prevents the model from using more trucks than exist. It also makes trade-offs visible. When the fleet is tight, priorities and repositioning decisions matter more. This slide shows a network flow model for terminal truck dispatching. Operationally, the diagram helps you see the time-expanded structure. Nodes represent location and time, arcs represent moves, and the model decides flows to satisfy service while minimizing cost. The concrete example has 3 containers. One goes from berth to storage with priority 10 and time window 1 to 3. One goes from storage to rail with priority 15, and time window 2 to 4. One goes from storage to gate with priority 8 and time window 1 to 4. With 2 trucks and 1 period travel between adjacent locations, the plan minimizes weighted completion while respecting time windows and fleet limits. Operationally, this example shows how the model uses time windows to decide which jobs must be handled first. Tier 2 uses iterative auction rounds. Containers bid for truck service based on urgency and travel efficiency. Trucks evaluate bids and assignments are selected to maximize system utility. Operationally, auctions support dynamic arrivals. When a new request appears, it enters the next round and competes for capacity, which is a natural match to a terminal environment. This slide presents the architecture of the auction-based approximation algorithm. Operationally, architecture matters because you need a fast cycle. Collect bids, evaluate them, assign tasks, and update truck states quickly enough for real-time use. This is the first code segment for auction dispatching. Operationally, focus on how bids are computed, because that is how urgency and distance are converted into a comparable score. This segment continues the implementation. Operationally, pay attention to how ties and conflicts are resolved. If 2 containers bid for the same truck, you need a rule that keeps the overall system stable. This segment continues the implementation. Operationally, this is where truck state and availability are updated after assignments are made. This segment continues the implementation. Operationally, the code must ensure feasibility. A truck cannot be assigned 2 containers at once, and it cannot reach a destination without travel time. This segment completes the dispatching code sequence. Operationally, this is where you typically see output metrics and checks that confirm assignments meet time windows and respect the fleet limit. The reported approximation ratio is 1.5, meaning the solution is within 150% of optimal. Per round complexity is proportional to containers. Times trucks times the log of their product. Operationally, the point is that you can get near optimal decisions fast enough to run in real time. Tier 3 uses swarm intelligence to explore dispatching solutions. Each Dragonfly encodes a priority-ordered list of container-to-truck assignments with timing decisions. Static behavior supports local refinement, and dynamic behavior supports global exploration. Operationally, this helps when the search space has many local optima, and simple greedy rules get stuck. This slide shows the Dragonfly swarm concept for truck dispatching. Operationally, think of it as a population of candidate dispatching policies that evolve over iterations, learning better sequencing and assignment patterns. This is the first implementation segment. Operationally, focus on how a solution is encoded and how a candidate dispatch plan is evaluated. This segment continues the implementation. Operationally, pay attention to how exploration versus exploitation is controlled, because that determines whether the algorithm keeps searching or locks in too early. This segment continues the implementation. Operationally, this is typically where you see behavioral weights influencing how candidate solutions move in the search space. This segment continues the implementation. Operationally, track how constraint violations are handled. If time windows are violated, the algorithm must penalize or repair those solutions. This segment completes the code. Operationally, the output should be a dispatch plan that can be executed. Truck assignments, timing order, and performance metrics. The reported configuration uses 200 iterations and a population size of 30. Behavioral weights for separation, alignment, cohesion, food, and enemy are set to 2. The algorithm searches for assignments that satisfy time windows while reducing weighted completion time. Operationally, this is the time versus quality trade. More iterations can improve results but cost compute time. Tier 4 learns representations of terminal dynamics without labeled data. Contrastive learning learns which states are similar in time and which are not. The policy network uses learned representations to proactively position trucks and reduce response time. Operationally, proactive positioning is a major advantage. You reduce wait time before requests even arrive. This slide shows the self-supervised learning architecture for predictive dispatching. Operationally, the architecture links 3 pieces: an encoder for terminal state history, a contrastive learning objective that shapes representations, and a dispatching policy that acts on those representations. This slide introduces contrastive loss. Operationally, contrastive loss teaches the model to place similar temporal states close together in representation space and dissimilar ones far apart. That helps the model learn repeating patterns such as discharge surges and gate appointment clustering. This is the first code segment. Operationally, focus on how training samples are constructed from time windows of terminal state data. This segment continues the implementation. Operationally, pay attention to the definition of positive and negative pairs because that is what determines what the model considers similar behavior. This segment continues the implementation. Operationally, this is where the encoder network and projection head are defined. This segment continues the implementation. Operationally, focus on training stability and on how the learned representation is later consumed by the dispatch policy. This segment continues the implementation. Operationally, pay attention to how the model is evaluated. Even without labels, you can measure downstream performance in response time and throughput. This segment completes the self-supervised code sequence. Operationally, the goal is a representation that improves proactive truck positioning decisions. The reported reduction in average response time is 15 to 25% versus reactive dispatching. The improvement comes from proactive positioning based on learned temporal patterns, enabling faster reaction to ship discharge surges and gate appointment clustering. Tier 5 simulates the full terminal ecosystem in a synchronized virtual replica. It evaluates multiple dispatching strategies under uncertainty before committing resources. Operationally, this supports rapid decision-making during disruptions, because you can test alternatives in simulation instead of improvising on the yard. This slide presents the digital twin architecture. Operationally, architecture includes synchronization of truck positions, crane workloads, gate queues, and rail capacity, so the dispatch plan is consistent across subsystems. A ship arrives 2 hours early while a key rail crane fails. The twin simulates 50 strategies in 30 seconds and selects the plan that minimizes delay while preserving safety. Reported outcomes include 30% faster response time, 22% better resource utilization, and 18% lower container dwell time. Operationally, this shows why simulation-based planning matters under uncertainty. Tier 6 uses distributed agents for trucks, cranes, containers, and infrastructure. Agents negotiate assignments using protocols such as ContractNet and auctions. This reduces single points of failure and enables emergent coordination. Operationally, distributed control can keep the terminal functioning when central schedules become invalid. This slide presents distributed intelligence and negotiation for dispatching. Operationally, the key is structured communication. Agents need a shared protocol to avoid conflicting decisions, such as 2 trucks attempting the same pickup. Negotiation for an urgent container completes in 2.3 seconds. Reported benefits include 25% reduction in communication overhead and 40% better fault tolerance. Throughput increases by 15% through emergent route and platooning behaviors. Operationally, this means agents can coordinate faster than a centralized system under load. Tier 7 combines human dispatcher judgment with explainable artificial intelligence recommendations. The interface provides confidence metrics, alternatives, and counterfactual what-if explanations. Human feedback is captured to improve future dispatching recommendations. This slide focuses on the interface. Operationally, a good interface prevents 2 failures: blind automation that operators distrust, and pure manual dispatching that cannot keep up with system complexity. Reported collaboration outcomes include 35% improvement in decision accuracy and 50% reduction in training time for new dispatchers through tutoring. Operational flexibility increases by 28% through adaptive learning from human expertise. Operationally, the key is that collaboration improves both performance and resilience. This practice question asks you to formulate a complete model for 3 trucks, 5 containers, and 4 locations, with priorities 15, 8, 22, 10, and 18. Travel times are 2 to 5 minutes, and you minimize total weighted completion time. Subject to capacity and timing constraints.